Hi, welcome everyone to this talk. My name is Stephan Ewen. I'm one of the co-founders and CTO at Ververica, the company founded by the creators of Apache Flink. And I'm also one of the co-creators and PMC members of the Apache Flink project. I'm here today to talk about some work we're doing in this project in the space of stateful serverless. So I'm going to talk about, stateful serverless and the elephant in the room. Thanks for joining. So when KubeCon was originally scheduled as a physical event, and I was starting to make my slides, I had some introductory motivation slides, but then I came actually across something really nice a few days ago, and which actually captures the motivation much better than what I had initially laid out. So I just decided to borrow that instead. It's a quote from Kelsey and a Dilbert comic, and yeah, what they're basically saying, if I can try and sum it up in my own words, is that there's been a lot of really cool work done in projects like Kubernetes about modernizing the infrastructure layer. But it's also very important to invest on the application layer. So the ways we build the applications above the frameworks, the paradigms, the libraries. Because otherwise we're going to end up with really cool infrastructure and still, not really well-built scalable applications. So trying to maybe illustrate this in my own words, what they're saying here is, if we're starting out with a non-scalable application, working together with, let's say, legacy database and so on, and we put this on top of a really cool infrastructure. No matter how fancy features of that infrastructure we use, we're pretty much still ending up with a non-scalable application. And so the idea in this discussion that Kelsey mentioned there is we should probably be looking, or at least that's how I understand it. We should probably be looking for something in the application layer. Also invest in a new application frameworks and libraries and so on to kind of have a way to make applications developed on top of these frameworks, which may or may not build on systems like Kubernetes. Something like magically scalable. It's probably not going to be that magical in the end, but just look at application frameworks and libraries that help build these distributed scalable applications. And scalability really is only one aspect. I think that's being mentioned here. There's a lot of other aspects that matter as well. Of course, there's the scalability to computation and state. There's consistency of the application, security, observability. A lot of things that currently, despite all the efforts on the infrastructure level, we still have to worry a lot about during the development of the application layer. And that is very much what I would like to talk about today, and like an idea in which direction these distributed application frameworks and libraries could go. And we're building a project that falls into this category in the Apache Flink project called Stateful Functions. That's looking at some of these aspects, not all of them. I don't think it's yet the holy grail, but it has some very interesting ideas, some very interesting directions and thoughts that I would like to share, and hopefully also get some comments and feedback on from the community here. So the project we're doing initially focuses on, let's say, those three aspects of the problem space. How to build applications that inherently scale compute, state, and also deal with consistency of state. Consistency meaning, do not get corruption or duplicates in the presence of crashes or network issues and so on. So the talk title says stateful serverless and the elephant in the room. So stateful serverless is really kind of a way in which we're thinking to build this abstraction. We're actually working on top of some of the serverless work that's being done both as part of, for example, the Knative project, or you can use this together with serverless technologies from cloud providers like with AWS Lambda. The other part of the title is the elephant in the room. So what is the elephant in the room here? And while we were working on this project, one thing that we came across repeatedly is that a big part of why, and my personal belief, we're still struggling with aspects like scalable state and consistency and so on altogether, is that we're somehow still relying on a bit of an age-old model with the traditional request-response databases. It's not saying databases are a bad thing here; they're actually a pretty amazing thing. But I think we have to rethink a few aspects of the database to make it like a really fitting player for this effort of inherently scalable and consistent applications. That's what we're trying to do in the Stateful Functions project. So one way to maybe give an idea in which direction it goes is a lot of the ideas you can think of are motivated by this paper that's already, I think, 15 years older or something like that, but it actually is. It's always a pretty influential papers. Like some of you may have come across it. It has been pretty popular. It's a while old, but it's a bit like a Bob Dylan song. It's like it has some timeless truth in it, and I hope that Pat Helland wouldn't kill me for summing it up in such a simple way. But it in my words, it advocates for building applications based on stateful event-driven entities or stateful actors. And in some sense, that's really the core of what we're trying to do. So to explain really the ideas that we're trying to bring into this stateful serverless space here, let me introduce you to the Stateful Functions project. First, describe what it is, and then give a brief example of how you can use this to build applications. So Stateful Functions, the subtitle is a mouthful: polyglot event-driven functions for distributed stateful applications. I'll try to break this down into a few more digestible units over the next slides. Yeah, as mentioned in the introduction, the core idea is to try and build like an API framework that helps with building distributed stateful applications with inherent scalability and consistency. And very much like the motivation in that paper that I mentioned, we're starting out with a building block that's, as the name also suggests, functions. So the idea is to model applications as very fine-grained functions that represent entities and really represent them at a very fine-grained level. Let's say there's one function for each user that is currently that exists in your system. There's one function for each, let's say, inventory item in your warehouse. There's one function for each parcel being delivered at the moment or so. So a very fine-grained management where a function really corresponds to an entity, not really a group of entities with like diverse types of state. It really encourages to model it in such a fine-grained way by assuming that as a function doesn't consume any resources when they're not invoked. And yeah, in some sense, it bears some similarities to, if you wish, also actor programming with a similar fine-grained modeling mechanism. The really crucial thing here is, as the other part of the name stateful function suggests, is the stateful nature of these functions. So each function contains or has access to local state. You can almost think about it like a local variable. Each function can access a local variable to look at its current state, and it has access only to that little bit of state. So let's say the function modeling the the tennis socks inventory item only has access to that particular state at any point in time, but it has access to that state exclusively and consistently. And then these functions basically message each other. Again, very much like in actor programming. So you can, if you want, think of this whole thing a bit like a transactionally consistent virtual stateful actor system. Stateful actors in the sense of stateful functions that message each other arbitrarily, virtual in the sense that you don't have to assume that they occupy resources when they're not active. So they're not like standing threads or even entries in memory. and consistent, because messaging and state are like transactionally integrated. You don't have to worry about messages getting lost, getting duplicated, state getting messages and state getting out of sync, and so on. So all these issues like retrying or working with taking care that state updates are either idempotent or retracted, you don't have to worry about these things. The way we're building this is it might be a bit surprising initially, but it actually doesn't have a database behind it. Instead, it actually rather than proxying all the state into a database, it's actually working based on a distributed snapshot model. So between all these functions that are there with all the state, the system draws a snapshot across all these functions, and this snapshot is consistently taking care of current state and in-flight messages and so on, to make sure that if we use this to recover from a failure, we don't duplicate or lose messages or anything. Communication with the outside world is with event ingress and egress. So this is strictly an event-driven system, and also this integration with the outside world is strictly transactional. So picking up events from the ingress, sending them between functions, updating state, and sending out messages through the event ingress is inherently transactionally safe. So you don't have to worry about sending duplicate messages to the outside world or compensating for any loss or change of state during failures, which is a pretty neat property that actually gets rid of quite a bit of complexity. How does it look like if you use a system like this? What components does it consist of if you deploy it? And it consists pretty much like a classical disaggregated architecture with the state and the database and the stateless application logic of these two parts also. We have the stateful part, which is the stateful functions cluster running on top of the Apache Flink system. Here, instead of a database and being subscribed to the ingresses and the egress streams, and then we have our functions, which we can deploy in pretty much any way that we can deploy stateless piece of computation with. So we can put this in a container with a request handler, HTTP request handler behind a service, and then deploy it on Kubernetes. We can take these functions and put them onto something like a function as a service platform like AWS Lambda, or we can encapsulate them in a different way behind a microservice endpoint. And the interesting thing to notice here is that these functions really are, even though they act in a stateful way, they are actually completely stateless. All state that they work with is always supplied to them on demand as part of the invocation and as part of the message. So state and messages are given to the functions basically together as one unit atomically. And that makes the functions themselves really, really pure and stateless. So they're very easy to scale. They're very easy to maintain. You can really operate them like a pure stateless application. There's one core aspect in here in this philosophy that I want to highlight, which is very interesting. And it goes back to this whole elephant in the room, the database. We have to rethink a few of these aspects there. And I try to explain it maybe based on this slide. There's a slide typo on the left-hand side. The second stream of input events should actually be the result or output events. Sorry about that. So if we look at a traditional database based architecture, computational part and database part, we typically start in the application. The application receives either the event or it receives the HTTP request or any other form of request with which it is invoked. And then it talks to the database and updates the state, gets a confirmation or a failure, deals with that, and then it usually responds to the request in some way. Now, what we're doing in the Stateful Functions project is actually something slightly different. We're sort of turning this upside down. we're saying everything starts actually in the database, if you wish. The database is the part that receives the events and manages the state, and then it invokes the application logic with the state and the events together. And it can decide when to invoke the application logic. For example, when nobody else is currently working on that state, so to make sure that that state is exclusively used. So in some sense, we're changing the role of the driving party of the application from the application logic to the database. And the part that reacts is the other part. Not the database reacts to requests from the application, but the application actually reacts to requests from the database. That might seem a bit strange and unimportant initially, but it has some really interesting properties that help with solving some of these problems. It might not be a match for like every possible situation, but when you can actually try to make this assumption, it actually can simplify a lot of things. Let's look in detail actually what happens if an event flows through such a system. And going back to this example of the shopping cart. So let's assume some user, Kim, wants to add some socks to her shopping cart. So we'd receive an event designated add the type cart for Kim to add socks. And the system would initially route this event to the shard that owns that shopping cart. It would retrieve the state of the shopping cart and then supply the state and the message to the function together. The function would decide what to do with it. Typically, in this case, just add this item to the cart and then respond with the updated state and a set of messages that it wants to send out, which goes again back to the system. So the system will then update the state and send the event, and it will make sure that this is a transactional unit. So there's no failure, cannot be no failure in between. Once the function responded and this response has been accepted, you're safe. And then these events are routed to the shards that are responsible for owning, in this case, the line item or the inventory entry for the socks. And in this case, we're invoking again the function with the current state, which is, let's say, the current stock, and the action like withdraw or reserve 3 items from that. So the important thing here would be that everything is driven by the system that in one unit manages state and messaging together, and the functions really become kind of pure. And even though they're stateful, you can pretend they're stateless. They are only stateful because state is supplied as part of the invocation on demand. If we try to now deploy such a system, what parts would we need? How does this look like actually using it on infrastructure like Kubernetes? So we would actually need the logic of the functions, which we would put, let's say, just on a deployment and create a service in front of them. We can even put a horizontal autoscaler around them if we expect varying load. And then we would have our stateful function deployment. That's an Apache Flink deployment consisting of several processes. It's actually a deployment here, not a stateful set, because Apache Flink doesn't really work with like stateful volumes or anything, but instead it is persistence by snapshots through something to something like S3 or HDFS or so. So this is another part that we need, but it's an interesting architectural choice, I think, because it makes some things actually quite simple to not deal with these persistent volumes and stateful sets. The Apache Flink cluster is also subscribed to the ingresses and egresses in order to receive the messages and send the messages. And the same thing actually, maps pretty well also to other infrastructures. Like if we, for example, would like to run this on the Amazon stack or so, we could just put our functions in Lambda. We'd have an API gateway, snapshot to S3, and ingress and egress with Kinesis. All right. So let's actually look at a concrete example. How would we, for example, build a billing application based on this? It's a very simple example in order to make it suitable for a short demo here. What we're assuming is we're getting events about changes to the subscription status of a user. Let's say grabbed through change data capture from something like the central user management database. We would actually have a stateful function where one function is subscribed to this set of events, being a user function. And this user function maintains, state like what's the user ID, the subscription status, and the billing interval. Now, billing is something that doesn't happen all the time. So the first thing we actually need to do is, when do we want to do the billing? Let's say we do it end of the month or beginning of the month always. And because we want functions only to be active when they really do something, the first thing we do is we actually schedule a triggered payment message for, let's say, for the end of the month. So the function can go away, and then this scheduled message is also part of the database and messaging system, and basically re-invokes the function at this end of the month point. In which case the user function would say, okay, I'm actually sending a new message with let's say a generated payment ID or so to a payment function, which if no function for this specific payment ID existed before, it will be created. And this function would own the state of the current payment processing. Let's say we've issued a request to the payment provider, we've not yet heard a response, or maybe it has failed twice, we're trying to retry it later today. Otherwise, we're assuming that it failed for this month. So like the stateful processing being part of another function. Here's a quick glimpse at a good part of the code. It's not a lot of code that this application needs in the end. Without going through every line of code, the really important thing I want to point out here is that you can see it's just a bunch of actually messaging. For those of you who recognize protocol buffers, you'll see a bit of protocol buffer packaging and unpackaging. Messages in stateful functions are inherently protocol buffers, so the system itself doesn't actually really see anything except the target address and some bytes, and then the target functions unwrap and wrap it into a protocol buffer any messages. And then this application really accesses just the state, pulls out state, sends a message, and then is done with the state. So for let's see this in action actually. So we've deployed this on a sample Kubernetes cluster. There are a bunch of pods running here. There's the stateful functions master and worker processes, which are the equivalent of the database of the state management system here. We have two more deployments for the payment workers and for the subscription workers. These are the two functions that I just explained in the example. We put them in separate deployments here. We could have also put them in the same deployment. They're just different request handlers invoked through HTTP, and through different we can through different URIs also have them in the exact same deployment. There's a log that actually shows the output of the payment worker, which we'll use for a later part of the demo. So we can't see a lot happening here, but there's sample data flowing around in the background, some payments being processed. Switching to the Apache Flink UI, this is the main operator from Flink's perspective that handles the stateful functions, and we can see from the different parallel charts a few hundred events per second going through. It's a very tiny deployment just for the sample case here, and I think we're far underutilizing it. We can use this, you can use all of Flink's tools to diagnose this application. For example, we can look at the back pressure. If our functions cannot keep up with processing the events, then Flink will eventually back pressure the whole system back to the ingresses and not pick up events anymore from there. All right. So one really important thing that we wanted to talk about is the consistency. And for payment provider, consistency is really important. We don't want actually to trigger multiple payments for the same user. That's a really embarrassing thing. Then we have to handle it. So we can simulate actually what happens if a duplicate payment happens. And we can see it in the bottom right window. We injected accidentally a duplicate message, and we can see that the payment functions immediately pick up this consistency deviation. There's a response from the payment provider about a payment we didn't actually even initiate. So we can try this another time. So this is just to show you that the system is actually built up to detect, or our sample application detects these inconsistencies. So usually these inconsistencies can happen pretty easily if you talk to the outside world, let's say send some messages to Kafka and also update database state. So if you actually crash everything at the same time, you usually have to take some care in order to not have any duplicates. But here we can really just crash all pods at the same time, get them restarted, and we can actually see from the logs that we cannot detect any inconsistency. Like, we didn't really get our internal state and the messages that we send to the outside world out of sync. And this is really because the state updates, the message sending, it's all inherently transactionally integrated. So you don't have to worry about duplicates or anything there. Yeah, that's actually the end of the short demo, and that's also the end of the talk, pretty much. I hope you enjoyed it. What I really want to to tell you today is this idea of the Stateful Functions project, trying to help build distributed, scalable, consistent applications, and it combines these two ideas: this idea of a programming abstraction based on stateful entities and a distributed architecture that kind of rethinks how to use databases, and in this case doesn't use a database. It uses like an event-driven system like Apache Flink. You can think of it almost as a combination of a database and a messaging system in one, and by doing that we can actually get some very interesting results. So I want to acknowledge also very quickly a few other folks that work on this project. I'm the one giving the talk, but this is really developed by the Apache Flink community, and especially those 4 folks here deserve a special shout out for being the ones that make this project great. So thank you very much. And that is it. I'm very happy for you to attend this talk and show some interest in what we're doing here. Thank you very much, and I'm happy to take questions.
Hello, yeah, hi. So thanks for listening to the talk. There's a bunch of questions that were asked in the box. Let me actually go through them one by one. The first question that came up is, how do you differentiate stateful functions from cloud state? I think that's a very good question. There's a lot of, I think, similarities between the two projects in the problem that they want to solve. They both try to give you this stateful serverless abstraction where the application gets this consistent state by notion of integrated state and messaging. There's a few differences, though. I think the way that you define functions it follows slightly different philosophies. So in stateful function, basically a function is an HTTP request handler, or if you use an SDK that is included in the project, you can basically just implement a function annotated with the let's say with the type and namespace, and then the SDK's request handler will actually invoke that function. I'm not an expert on cloud state. I think it's a gRPC protocol that you develop in cloud state if you want a stateful entity there. So there's a few differences. I think the approach that we picked in stateful functions has this nice advantage that it works pretty easily to actually put this also behind something like an API request gateway on Amazon and run the actual function logic as a Lambda function as a service, or similarly on Kubernetes to put this in a similar deployment, put it behind a service and scale it independently. I think the model that Cloud State uses is that you strictly deploy these functions as sidecar containers to the system that manages the state, which in this case is Akka cluster. Talking to a database in the background that does the persistence. So if you wish, yeah, I mean, TLDR, I think the differences are the decomposition between state and compute is, I think, different in stateful functions, and other than that, the stack is different. In this case, it's Apache Flink. In the other case, it's Akka plus some database that Akka persistence can talk to, like Cassandra, for example. There's another question. Is a stateful function like an object from object-oriented programming, encapsulating data and behavior? I guess you can think of it like that. I personally like to think of it more as an actor. So the notion of processing messages or methods of the function being invoked only one at a time, one after another, at least per entity key. So I think different. So there's no parallelism. But yeah, other than that, I think the differences are probably the same as you would say that are the differences between an actor and an object from object-oriented programming. The other thing maybe worth pointing out is that an object from object-oriented programming, like in the naive way, it's always around. It's sitting somewhere in your heap memory, versus a function isn't really active unless it's invoked, right? The only thing that, let's say, permanently exists is the state entry in Apache Flink, and when a message for this function comes, then the state is pulled out, and the state and the message are delivered to the function. And for example, if this function is running on a function as a service provider, you may not have any resource occupied unless really a message comes. There's one question: would it work for multi-tenancy as well? Something like multiple users making the payment in absence of a database who handles those. I'm not 100% sure what the second part of the question refers to, but multi-tenancy, you can use this in a multi-tenant fashion, I think pretty well. If you assume that let's say the administrator of the Apache Flink part of the system that that handles the messaging and the state, that subscribes to the incoming events, that this is like a trusted party, then the actual function code can come from different parties that don't really trust each other, because they're running a separate deployment, separate containers. They cannot really interfere with each other. They don't have like direct access to state in the system and so on. They can really only communicate by sending messages, and thus they cannot really interfere with the other functions, and they're running in separate processes. So we haven't really yet spent a lot of time designing it into a strongly multi-tenant system. So there are probably a few quirks you'll run into in let's say setup configuration aspects that aren't absolutely optimized for multi-tenancy. But I think the architecture as a whole is pretty promising for multi-tenancy. Especially because the computation in different services is strongly isolated against each other, which is a very big part that makes, for example, stream processing or other systems where code from different parties really runs in the same system, which poses a big challenge there. There's a question: how would the migration to stateful functions work? That is a very interesting one. Like, how do you actually migrate an application to stateful functions? So it's a bit of a different paradigm, right? So it's not as easy as, let's say, swapping MySQL for Postgres or so underneath the hood and keeping everything else the same. If you do want an application to migrate to stateful function, you probably do have to rewrite it first of all. One thing that we're trying to add to the project is tools that help with, let's say, migrating the state from another application into stateful functions, meaning taking, let's say, a dump from a database and actually loading it into Apache Flink. So there's some early tooling for this already. It's called state bootstrapping, where you can actually you can take some input data and basically load it into what's called a save point for Flink, which is basically like a snapshot archive or so, and then you can start the whole application from there. But it's actually a bit of an involved procedure. So you actually have to write an Apache Flink data stream application for that at the moment to load the state in there. We're working on making this easier to add add tools like, just issue a SQL query in order to import basically state into stateful functions. Stay tuned. There's going to be more releases in the future that will make this easier. There's one question. Do you have detailed comparison of your approach to scalable state to other approaches, pros and cons? As a scientific evaluation, I don't think we do have that. There's a conceptual, like a pretty strong conceptual difference here that I try to motivate in the introduction, like this, switching the roles between application and database in terms of acting, reacting, which the programming model also inherently means that you really distribute by entity. Because each stateful function by its address and so on can basically live anywhere. I think these are very good starting points for like a detailed comparison. I don't know. I think if somebody is looking for a research project, someone in academia or so, I think this would actually be a very interesting one. I personally don't know that something like this already exists. I think we might have time for one more question. Here's another one. How high is the memory consumption of Apache Flink? So Apache Flink is developed in Java, so there is a certain amount of memory consumption that just comes with the JVM. Flink itself, I think you can kind of comfortably run the framework with something like half a gigabyte or so. So the let's say the main part of the framework, the coordination part, I think if you give it 100 megabytes, it should be actually fine. And then there's a good amount of memory that should go to the embedded RocksDB instance, which is where the local state index is stored. So this should always have, I would say, maybe roughly half a gigabyte of memory for decent performance and so on. So yeah, the memory footprint of Flink is pretty much that JVM with embedded RocksDB. You can think about it like that. So half a gigabyte is a good start. More obviously always helps with performance. There's one more question. I'm just going to keep going unless the organizers cut me off here. So how do you handle synchronous communication, like getting errors? How do you deal with synchronous communication here? So there's I think there's two answers to that. Just got the message. This is our last question. Sorry about that. If you actually deploy this in a way that your function invocation can easily block, because you can spawn a lot more processes that handle the different invocations. Like if you put it, for example, on a function as a service platform, then just do synchronous communication in the function. It doesn't matter if it blocks. If you actually are limited to the number of processes you have, then you have some facilities in stateful functions to actually do asynchronous requests and asynchronously handle responses. So that's pretty, I would say, pretty much how in many reactive systems you do external requests. In terms of consistency, how do you do synchronous requests if you were worried about consistency? You wouldn't. All external communication should actually go through egress events. If you do that, then consistency comes out of the box. If you do external communication that affects side effects from within the function, then basically it's your own game to worry about consistency again. All right. That was it. Thank you very much for listening and these very interesting questions. Very, very cool. There's a Slack channel, KubeCon Serverless. If you want to ask further questions there, I'll be in that Slack channel for the next hour or so. So feel free to also ping me there if you have some follow-up questions. Thanks a lot for listening, and yeah, I'm very happy for you guys attending the session and asking these questions. Thanks a lot.